Hey folks, welcome back to Combo Class. I'm your teacher Demotro, and today we're gonna look at some crazy types of numbers. Now, you might think, why would we need all these weird nicknames for numbers? Because they do have technical definitions we could write them as, but there are some times where having a nickname can be like a good handle on a tool that can help you accomplish a lot. So before we look at all these weird nicknames and some of the surprisingly deep applications of some of them, let's look at some more common nicknames in math that have come in handy for us before. Now, in this episode, when I talk about numbers, let's assume that I mean what's called a natural number, a whole positive integer that could be a number that you've used to count something, like how many dice I have in this box. All right, let's look at some nicknames. Some of the ways we nickname numbers are based on shapes we can arrange them in. Like the number 9 can be considered a square number because we can arrange 9 dice into a 3 by 3 square. Now, the number 10 clearly can't fit into a square, but it does fit into a sort of triangular-ish shape, along with the whole family of numbers that go 1, 1 plus 2, 1 plus 2 plus 3 plus 4, and so on. So we call this type of number triangular numbers. What about 11? It's not a triangle, and it's also not a square or any type of rectangle except a super long, thin one, because 11's the type of number that can't fairly be split into side lengths or piles apart from 11 piles of 1 or 1 pile of 11. And we could have just called numbers like that integers with 2 factors, but we nicknamed them prime numbers, and I think that term came in a lot of handy over the years. What about 12 though? Not only could 12 be arranged into a pile of 12 or 12 piles of 1, it could also be arranged into 2 piles of 6, 6 piles of 2, 4 piles of 3, or 3 piles of 4. And if we counted up how it had more types of pile we could split it into than any smaller number, we would come across a nickname like highly composite numbers that we talked about in an early episode. But what if we were looking more at all of the different sizes of pile we could possibly divide it in? And we tallied up, we could make 3s, we could make 4s, we could make 2s, we could make 6s, we could make 1s, and we're not going to count 12 because that's the number itself. Well, if we added up all those numbers instead of just seeing how many there were, that's something called an Aliquot sum. And it turns out to be what all those weird names of number I showed earlier have in common. Technically speaking, when we're looking at a number's Aliquot sum, we're adding up all of its proper divisors, which are its factors apart from itself. So this is sort of a deeper way of looking at primes versus composites, because any prime number only has 1 as its proper divisor, and so any prime has an Aliquot sum of 1, and composites will have different numbers greater than 1 as their Aliquot sum. So now let's start with a simple look into those different types of composite Aliquot sum by wondering which numbers have an Aliquot sum that's bigger than them, and which ones have an Aliquot sum smaller than them. So numbers with an Aliquot sum less than themselves are called deficient numbers. Man, they really roasted those numbers. And numbers with an Aliquot sum greater than themselves get to be called abundant numbers. And in the middle, if we have any numbers where the Aliquot sum is exactly equal to themselves, those are called perfect numbers. And there are some of those, but they're rare, and they're important enough that those will come up throughout this episode. So, how often do deficient or abundant numbers occur? Well, it turns out as you go up the number line and scan greater and greater portions, looking at what's known as the natural density of these types of number, the amount they occur does approach some sort of constant. As you look at bigger and bigger chunks of number line, you will find that abundant numbers happen about a quarter of the time, but really somewhere in this range. They're not sure exactly. And deficient numbers happen somewhere in that range, and perfect numbers are rare enough that their natural density is known as 0%, meaning as you look at bigger and bigger chunks of numbers, they will occur less and less frequent, approaching 0%. So there's all sorts of deficient numbers, including every prime number and other numbers, and there's all sorts of abundant numbers, even or odd, although the smallest odd abundant number is 945. And you can even take abundant numbers further by categorizing different ways of numbers that have the most abundance. So there are terms called highly abundant numbers, superabundant numbers, even
colossally abundant numbers.
But these lists have so much in common with another way of looking at numbers that are superfactorable called highly composite numbers. And I already made an episode about those you can check out, so I'm not going to go too deep into those super or colossal abundant types of numbers. We have enough other ones to talk about. So on the thin line between abundant and deficient numbers, perfect numbers where the proper divisors add up exactly to themselves are pretty rare. We got 6, 28, 496, the next one, and there are 51 of them we've discovered total. We don't know if there's an infinite amount or not, but we'll get back to perfect numbers later because these are kind of an underlying theme of the episode. The first mutant variation of those, which are more common than perfect numbers, are semi-perfect numbers, where some subset of the proper divisors add to themselves. Like for 12, all of the proper divisors add up to more than themselves, but if we skip the 4 and add the rest, it does add exactly to 12. So 12 is not perfect, but it is semi-perfect. And that brings us to weird numbers, the name for numbers that are abundant but not semi-perfect. Or in other terms, their proper divisors add to more than themselves, but no subset of them add exactly to themselves. And if you tested the first 69 numbers, you might think that no numbers were weird. But 70 is. It's the lowest weird number because its proper divisors here add to more, but none of these can add to 70 exactly. The next one's 836, then 4030, so weird numbers are not super common. Now, beyond semi-perfect numbers, we get multi-perfect numbers, which come in different types. We could have a 3 multi-perfect number or a 5 multi-perfect number. So a k multi-perfect number means that all of its divisors add up to k times the number. And so the number is defined in terms of all of its divisors, but we could also say that its aliquot sum is k minus 1 times the number. So a 1 multi-perfect number would just be the number 1. That's the only proven candidate for that. And 2 multi-perfect numbers are regular perfect numbers, 51 of which we've found, and we don't know if there's an infinite amount or if there's any odd ones or other stuff. But what about beyond that? 3 multi-perfect or 4 multi-perfect numbers? What's up with those? For 3 multi-perfect numbers, where the aliquot sum is twice the number, or named that way because all of the divisors are 3 times the number, 120 is our smallest, and that's our biggest, and these 6 are conjectured to be the only 6 3 multi-perfect numbers. A lot of mathematicians think the list stops there. However, if we were to find some rare things such as an odd perfect number, which we don't know if they exist and it's unlikely but they could, there are ways that this list could possibly be expanded. But many mathematicians think there are only 6 3 multi-perfect numbers. In fact, many mathematicians think we've categorized every single 3 multi-perfect up through 7 multi-perfect number. So let's check out some of the 4s and beyond. Here's a little chart where we can see the smallest 3 multi-perfect, 4 multi-perfect, 5 multi-perfect number, and beyond. And here's the conjectured total amount of each type of multi-perfect. Like there's 1 multi-perfect number, don't know how many 2 multi-perfects, 6 3 multi-perfects, and we're pretty sure on these amounts up through 6 or 7, and then we start getting less sure, might be a few more 8s than that, and we're pretty sure we don't know all of the 9 multi-perfects, just some of them. Now let's look at quasi-perfect and almost perfect numbers. Quasi-perfect numbers have an Aliquot sum that's one more than themselves, and almost perfect numbers have an Aliquot sum that's one less than themselves. And quasi-perfect numbers are so rare that we haven't found any, and we aren't sure if any exist. So we've searched a lot of numbers and shown through proofs and computer trials that if a quasi-perfect number exists, it has to be an odd number, a square number, and greater than 10 to the 35th power. But we're not sure if any exist or not. Now, as for almost perfect numbers, where the Aliquot sum's one less than themselves, we do have some of those we know, like 1 technically has that trait with a 0 Aliquot sum, and 2 with a sum of 1, and 4 with an Aliquot sum of 3, and 8 and 16. And it does turn out that all the powers of 2 are almost perfect numbers, but we haven't proven if those are the only almost perfect numbers, or if some other number eventually sneaks into the mix that's not a power of 2, but is almost perfect. So all of these weird names we've learned so far have had something to do with numbers' Aliquot sums, adding up their proper divisors. So what would happen if we did this process repeatedly, in an iterated way, where we took a number, found its Aliquot sum, then found the Aliquot sum of that, and then the Aliquot sum of that result, and see where it spiraled? Well, if we did that with a perfect number, it would just stay on that perfect number. The Aliquot sum is itself. But other numbers do interesting things. Now, what we're doing here is known as an aliquot sequence, a sequence where each term is the aliquot sum of the last. And a lot of numbers, like 24 here, go on a little spirally dance before they hit a prime, which sends them to 1 and crashes them to 0. But other numbers, like 25, which is known as an aspiring number, go to a perfect number. So aspiring numbers are the name of numbers that end up hitting a perfect number where they'll stay in their aliquot sequence. And other numbers don't hit a prime and don't hit a perfect number. They go on a little loop. We can define aliquot sequences that loop based on how long their period of looping is. Like if they have a period of 1, that means their aliquot sequence sends them to themselves instantly. That's our perfect numbers. And if they have a period of 2, where one number has the aliquot sum of another that has the aliquot sum of it, these are known as amicable numbers, the smallest of which are 220 and 284, and there's the next smallest. Now, if we have a period of 3 or more, these are known as sociable numbers, and we're still figuring out which of these exist and which periods or amount of numbers in the cycle are possible. For example, we've never discovered any loops with a period 3 cycle. We have discovered some with period 4 cycles, the smallest of which is there, and we've discovered exactly and only one period 5 cycle, which is right there. The only periods we've found, or lengths of cycles that numbers can loop in this way, are 1, 2, 4, 5, 6, 8, 9, and 28. The period 28 one actually has surprisingly small numbers. Its lowest term is that. So any number seems to either be a prime or crash into a prime, which sends it to 1 and then 0, or be a perfect number or an aspiring number that crashes into a perfect number, or be an amicable or sociable number with a loop, or perhaps some number that flies into one of those loops. But there's some gaps in the fun nicknames. Why do these ones get nicknames and those ones don't? So I'm gonna make up some more nicknames. Who's gonna try and stop me? I'm gonna call numbers that would fly into an amicable or sociable cycle without starting in one extroverted numbers, kind of like aspiring numbers. So extroverted numbers would be a number that isn't in an amicable or sociable loop, but its aliquot sequence sends it into one. And what about the other type of number apart from these? The ones that crash into primes. Let's call those introverted numbers. Numbers that their aliquot sequence ends up terminating at 1. Now, this seems to be all the possible numbers. Is it? Well, It's actually an open question whether these are all the types or whether there are any numbers whose aliquot sequence keeps growing and growing and growing without bound. So in case that type of number exists, let's give it a nickname too. Let's call all these types of numbers containable numbers, and let's call, if there are any, the type of numbers that fly toward infinity with bigger and bigger aliquot sums, uncontainable numbers. One number that might be uncontainable is 276. Despite its relatively small size, we don't know what category of number it's in because its aliquot sequence gets pretty huge. At step 469, it's 45 digits long. And numbers that big get hard to factor and hard to figure out what the next step in the aliquot sequence is, so we don't know its current fate, or whether it's what I'd call containable or uncontainable. But although 276 might look pretty uncontainable, there are other numbers that have grown to a pretty big size before flying back down and turning out to be introverted all along, like 138. It starts growing and it grows to that number after 117 steps, but eventually it goes all the way down to 0 after 177 steps. So 138 might have looked pretty uncontainable, but all along it was introverted. Alright, let's move on from my silly nicknames to some more silly nicknames that are officially used by mathematicians, like untouchable numbers. Untouchable numbers are numbers that are no other number's aliquot sum. They won't ever appear as a successor in any aliquot sequence. The first untouchable number is 2, which is pretty easy to deduce why it would be untouchable. Like, any prime has an aliquot sum of 1, but as soon as you get past 2 and 3 to 4, that has an aliquot sum of 3, and you can't make any number whose aliquot sum is 2. Turns out 5 is the next untouchable number. And then there's this weird gap where every number from 6 to 51 is, I guess, what you'd call touchable. But 52 is untouchable. The pattern in these ones is pretty trippy. Alright, now to transition back to perfect numbers for our finale, because you may have noticed that perfect numbers have been underlying a lot of these, and a lot of these are sort of mutations of perfect numbers. Let's go to one fun, silly, transitional one called sublime numbers. Sublime numbers are numbers that have a perfect number amount of total divisors, including themselves, and those divisors add up to another perfect number. Like 12 turns out to be sublime because it has 6 total divisors, and those add up to 28, both of which are perfect numbers. How sublime. But this is a pretty rare quality because apart from 12, we've only discovered one other sublime number so far. And this is it. So bringing it back to perfect numbers, because all of these things were kind of mutations of that. Perfect numbers have some crazy superpowers. And just to touch the tip of the iceberg, let's look at some of the things we've proven about even perfect numbers. Now I have to say even perfect numbers, but we think those might be all of the perfect numbers. All of the 51 perfect numbers we've found have been even, and odd perfect numbers have these crazy unlikely restrictions we've proven about them, including that they'd have to be bigger than 10 to the 1500 power. So all of this is about even perfect numbers, but it's very likely it's about all perfect numbers. So let's look at the first perfect numbers. 6 can be turned into dots of a triangle, a triangular number, where we're summing 1 plus 2 plus 3. 28 turns out to be a triangle as well, summing all the numbers through 7. 496, I didn't want to draw 31 rows of dots, but I could have. It's summing all the numbers through 31. Next up, summing all the numbers through 127. Now, not only are these triangular, but let's see which triangular numbers they were. 3, 7, 31, 127. If you paid enough attention to these numbers, you'd notice that, for one, they're primes, and for 2, they're 1 under a power of 2. And these primes that land 1 under a power of 2 are so important they have a good nickname named after a mathematician named Mersenne. They're called Mersenne primes. And these Mersenne primes turn out to have a 1-to-1 correlation with even perfect numbers. For every even perfect number, there is 1 corresponding Mersenne prime, and vice versa. This means that like we found 51 even perfect numbers, we've found 51 Mersenne primes. And if we ever find one more of one of them, it's one more of both of them. And if we ever prove that one of them is a finite or an infinite series, it will prove that about the other as well. But those are unsolved questions. And there's an even closer link between Mersenne primes and even perfect numbers. Because if we factor any even perfect number, we get some power of 2 multiplied by some Mersenne prime. Now, these Mersenne numbers turn out to have so many weird superpowers, and the 8 biggest primes we've found so far are all Mersenne primes. So I'm going to dedicate a whole episode to Mersenne primes in the near future, and I'm sure we'll see our friends' perfect numbers pop up again in that. But overall, I hope you enjoyed learning some weird nicknames of number, and you never know which ones might end up being important. If perfect numbers have such strange properties, what about all those other weird mutant variations of them? There are a lot of fun unsolved questions here, and who knows if you could be the one to solve some of these crazy unsolved questions. Find the first quasi-perfect number, find the first odd perfect number, find an uncontainable number, or prove that one of those doesn't exist. So nicknames can come in handy, and I hope you enjoyed learning about some numbers. I'll see you guys next time.